Well, hey everyone, and welcome back. This video is going to be mostly just clarifying a piece of information about folds that is sometimes quite easy to misunderstand. Previously, in most of my videos, I've been drawing folds in 2 dimensions, right? Just on 2D cross-sectional diagrams, or sometimes on block diagrams, I think, but those contain a similar look in that they're quite flat. So to start off this video, I just have a simple sketch, 2-dimensional, of a antiform, right? Because it's pointed upwards, it forms that A shape. It's an antiform, which of course we know is a fold and is formed by compressional forces pushing what was once a horizontal piece of strata upwards such that it forms this crest shape with 2 limbs that dip away from the crest. So that's easy enough to define in 2 dimensions, but when we think about folds in 3 dimensions, sometimes our brains just try to extend things out, and perhaps just by intuition we create this sort of just like an arc shape, right? Or, well, you just extend this arc outwards, such that we form sort of a tunnel. If we were to imagine this being hollowed out, then we would have an exit on this side, maybe something that looks like that. So, a person, if they were standing in here, they could walk directly through, just underneath it. This would stay at a constant elevation, you would just go straight through, right? So that's generally the misconception, that they would be something like a tunnel. However, in large-scale folding, in order to have this occur, we would have to have a very even amount of pressure applied across a very large area, right? Because when you think about it, when you're compressing things, in order to get this nice uniform shape, we would need the pressure to be even across this entire length, which in many cases is not true. Because folding occurs at convergent plate boundaries, right? That's where the plates are pushing together, there's a compressional force. You'll generally find that the forces, the compressional stress that is being applied is strongest on a very small given location, generally directly on the plate boundary. However, folds generally stretch farther than just the plate boundary itself, and because of that you'll see that they stretch farther and farther away, and as you get farther from this point of maximum stress, the stress is going to decrease. And what would this do to the strata as you move farther out? Well, you would get something like this. Instead of being folded up so at this rather steep angle, you might get something that just looks like a low, it's still clearly not horizontal, it's still clearly been pushed upwards, but you get this lower, more gently dipping arc shape here. So if we want to think about the effects of this and what this would mean as far as 3D goes, well then just think about it this way. If this is at the front of your antiform, then as you move farther back, as you move backwards in 3D space, remember we're working in 3D, so as you move backwards in 3D space, not along this direction or along this direction, but actually backwards, you're not going to have it stay at this nice even elevation. It's not going to be the same height as you move backwards. Rather, you're going to get shorter and shorter and shorter as you move back. So you would have to sort of connect a line that looks something like that, right? So if we were to make a quick edit, I think this will really illustrate the point. If we were just to make a quick edit to this diagram, this little sketch, then what we would see is that it would go backwards farther and farther back, right? Just imagine that there's some surface back here. Maybe that's the back of the fold. It's farther away, so I'm drawing it smaller. But maybe that's it, right? Then maybe we're going to have something like this, where it just goes back until it meets more or less the back of the fold. And then this would go back until it meets that point. And then we would just sort of connect that, and then since we're trying to make it a realistic 3D sketch, then we would erase what we can't see, right? And then we would get something that looks like this. So once again, if we were to imagine this as being hollowed out and you were to walk through this, then it would be more like a cave than a tunnel, right? Just sort of a little indent in the earth, and you would walk through, but quickly you would realize, hey, there's a dead end here. You'd end up right there, unable to go any farther, because you end up coming to this point where the fold has basically shrunken, and eventually it actually will become horizontal, meaning you're just left at a wall, really, and you can't pass through that, simply enough. And that's 3D folding in a nutshell. That's just really the theoretical piece. These sort of sketches you'll see aren't used in actual applicable working on geologic profiles and stuff like that. So I will elaborate on this further. I just think this was a good introduction to why folding in 3D works the way it does. So hopefully this was informative, otherwise good review. Hope you guys enjoyed, and I will see you all in the next video. Ciao.